Have any questions? I think there's a homework due today, isn't there?
Yeah, homework 5's due today. Can't say that I have questions yet. I read through it last week, and I just was looking at it here before we started. Can't tell if I'm muted or not. I don't think so.
No, I can hear you.
Okay. But I haven't really dived into it yet. So my apologies.
All right. If questions arise, just put them in. Just email me, or probably email me. It's easier. All right. Let me share my screen. On to the lecture. So last time we ended, we were talking about symmetric positive definite functions, matrices, and we got through some properties, and the fifth property was something called Choleski factorization. So let me repeat what that means. If A is symmetric positive definite, then there exists a unique lower triangular matrix L with positive diagonals and such that not only we have an LU factorization, but we have an L transpose factorization, where U is the transpose of L. Right, so that's Choleski factorization. And I was mentioning in passing that this is less expensive than LU by about a half. And you don't really need pivoting for stability here. All right, so let's go ahead and prove this if and only if. Let me do the easy direction first. The easy direction would be this direction. All right. If you do have a Choleski factorization, then let's check, first of all, A transpose is going to be L transpose transpose L transpose. That's L transpose, so that's A again, so you're symmetric. And secondly, let's check that you're positive definite. So let's look at the quadratic form for A. And we get this factorization. Now we can interpret this as an inner product of L transpose X with itself, right? So that means that it's the norm of L transpose X squared. Here I'm using the regular Euclidean 2 norm. But the key then is that this is certainly greater or equal to 0 because it's a norm. Um, but what about equality? When can it be equal to 0? And the idea here is that if x is non-zero, then L transpose X is also non-zero because L transpose is non-singular. How do you see that it's non-singular? Any thoughts?
No, this is normally where I get blocked.
Well, because L has positive diagonal entries, right? So in
Oh,
particular,
sure.
yeah. So in particular, the determinant of L, which is the same as the determinant of L transpose, is positive. All right. So we have that direction. So what about the other direction? Now we want to show that if you are SPD, you have a Choleski factorization. And again, this is a typical thing where we're going to do an induction on the sides. Okay, let me forget about the base case, etc. Let's just go ahead and set up the induction step. So I'm going to isolate the first row and first column. And I'm going to call the column, the sub-diagonal column L12, and then here the super diagonal row here L12 transpose, because A is SPD by hypothesis, right? So it's symmetric. A to 2 is going to be symmetric as well. All right, so, and let's set up the induction step. So with this kind of structure, we'd like to factor this as square root of A110 L12 over that square root times the identity 100 A22 tilde and square root L12 transpose over the square root 0 times the identity. All right, so that would be, this is the induction step that will basically reduce the factorization to dealing with this block here in the next step. Let's check what happens when we multiply this out. Okay, I'm going to do it in 2 steps. I'll keep the first here. First matrix, and I'm going to do the other product. So I'm going to get root A11, and then L12 A11. Here I'm going to get 0, And then I'm going to get A2. Agree with that? All right, and now let's do the other matrix multiplication. And so square root and square root, A11. And then here the square root nicely cancels out. I get L12 transpose. Here nicely cancels out L12. And finally, I'm going to get L12 transpose over A11 plus A2. Now, why am I allowed to take the square root of A11?
Positive.
Because it's positive, because A is SPD, right? This was one of the properties that we had last time. Let's see. Oh yeah, there it is, by 4, right? If A is SPD, then the diagonal elements are positive. All right, so that's good. So we're allowed to take the square root. And and when we do this triple product here, we do get back the form of A, except that we need to, in order to compute A22 tilde, we just have to solve here, right? That's pretty simple. So this implies A22 tilde is going to be A22 minus L12 transpose. And notice that, as I said, A22 is symmetric, right? And L12 transpose is symmetric as well. So this is going to be n minus 1 by n minus 1. Right, because we want to do the induction and we want to be able to just continue on A22 tilde. But the question is, is A22 tilde SPD? Right, so that we can use the induction hypothesis. All right, so here we need to recall a little bit some of the properties from last time. Remember, okay, I promised that we were going to use this first one. A is SPD if and only if X transpose AX is SPD for any X non-singular. All right, so that means in our context that, right, we can think of this as X, right? So then you have X here and X transpose over there. A is SPD by hypothesis, so that means that this middle thing is SPD. Okay, so by 1, the matrix this matrix is SPD, right? And then let's go back. By proposition 2, if a matrix is SPD, then all of its principal submatrices are SPD. Right? So in particular, we can take A22 tilde is a principal submatrix. So we get that by 2 from last time, A22 tilde is SPD. All right? Okay, great. So positive definite. Now we can use the induction hypothesis because we are doing an induction on the psi. So we know that for n-1 by n-1 matrices, it's true. If you're SPD, you have a Choleski factorization. So by induction hypothesis, A22 tilde is going to be L tilde transpose for some unique L tilde lower triangular with positive diagonal entry. All right, so now that means that A let's go and rewrite A. So that was √110, and then I had L12 over √A11 identity. That was my X transpose, or then I have 1, 0, 0, and then instead of A22 tilde, now I have L tilde transpose. And then here I have square root 110, 1. By the way, I didn't mention this, but this X or X transpose is non-singular because it's lower triangular, right? So here when I said by 1, this is SPD because X is non-singular. And this you can see because you can just take its determinant. Right, for triangular matrices, the determinant is just the product of the diagonal elements. And so here the product of the diagonal elements is just √A11. Stop me if I'm going too fast here. In any case, what do you think the next step is going to be?
Probably expanding out this factorization and finding that we get some L and LT for that are n by n.
Exactly. So how do we split this up? We want to give one of these guys to this matrix and the other one to the other matrix. So let's check if that works. So if we do root A11, 0. L12 root A11, and then we put L tilde here. Right, it needs just to check that when you do the matrix multiplication, you get equality here. But that's clear because let's see, is this clear?
Yeah.
Yeah, because we can split, as Justin was saying, we can split this as a multiplication of two diagonal matrices. And then we can give one to this and one to the other one. So yeah. All right. So and with that notation, then this is just L. All right. So great. So that finishes the material about positive definite matrices. Now, they are a very, a very large and useful class of matrices. So we'll see more of them. But there is another class of matrices for which you can improve the Gaussian elimination algorithm. And these are called band matrices. All right, so what is a band matrix? Basically, it will have entries A1, 2, and again, I don't like, I don't quite like this notation. So let me use my notation, 1, 1, A1, 2. And then it's going to go all the way to some index, which I'm going to call 1 plus BU. And then after that, it's going to be 0. So then likewise, in the other direction, A21, this will go all the way to A 1 plus BL 1. Then it's going to be 0 afterwards. So that's, that's kind of a band, a strip around the diagonal. And let's see what is this number here is going to be n minus bu n. And this number down here is going to be n minus bl. And 0. Okay, does that make sense? That's a band matrix, and BU and BL. So BL is the lower bandwidth, and BU is the upper bandwidth. Right. So I set it up so that if BU is 1, then that means you have one diagonal over the main diagonal, right? BU is 10, you have 10 extra diagonals over the main diagonal. All right, so in this case, there are some nice properties for band matrices in terms of Gaussian elimination, as you can expect. If, for instance, if A has an LU factorization, so no pivoting, then it's actually not hard to see that L will have the same lower bandwidth. And U will have the same upper bandwidth. Basically, you don't get out of the class of band matrices in this case. And rather than, do a formal proof, you can kind of draw a picture where you have a picture like this. This is BL and this is BU. They might be different. But as you can see, if you don't do any pivoting, then you're going to use the first row to eliminate the variable only in the first L places under the diagonal. And so those are the entries of L that you're gonna get, right? Only L entries below the diagonal. So you stay within the at each step you stay within the same class of matrices. And this type of operation will have a cost. You can count the floating point operations, and it's going to be 2n BU times BL. Plus, you're going to need to store things in memory, and that's the space needed. BL plus BU plus 1. All right, so sorry, I'm thinking I'm missing something there. There's an N missing. Yeah. No. I think there should be an N missing there. Right, because you think of it as a rectangle. This is the width of the rectangle, but then there's the length of the rectangle. All right, but anyways, I will not go into those calculations. Let's instead, let me tell you a little bit about partial pivoting. So for partial pivoting, means that you're gonna maybe swap some rows, right? So you're gonna do a permutation. But again, let's draw a picture for that. Let's say that we have this, right? And let's say that, so let's be more precise here. Right, so this is a row at some point in my band matrix. And here is BU, this is BL. And so if I did swap, then I would, I would add some non-zero entries up here. Right? But that's okay. So you're still banded. So U is going to still be banded, but we'll have upper bandwidth BL plus BU. So not the same bandwidth as before, but it's still banded. And L is going to turn out to be essentially banded. And what that means is that L might actually have some things under the diagonal, under the BL diagonal. But the number of non-zero terms below the diagonal will still be bounded by BL, actually BL plus 1. So this means E at most BL plus 1 non-zero entries diagonal in each column. That makes sense? So, in any case, rather than going into the details of these special cases, let's do an example and show how these things come up in practice, okay, why they are common. Okay. And the reason, one of the main reasons, is because they come up when you try to solve ODEs. So let's do an example here. So let's look at the following ordinary differential equation. So I'm going to take y double prime minus some function p of x, y prime, minus some function q of x, y, equals some function r of x. Okay, so this is for x in some interval on the real line. And let's also assume that we fix the values of y to be alpha and beta. Okay, so y of a, we have some boundary data, and then otherwise we just want to solve this ODE. Now it turns out that you have this, have certain properties. Let's assume that the function q is bounded below by some positive quantity. So q is bounded away from 0, from below. So with these assumptions, this ODE is a model for heat flow on a rod. We have a kind of a rod here, and this rod will have different properties depending on x, so different local properties. That's encapsulated in this p function and q function, and then basically y of x, then we should think of it as the temperature. All right, so we fix the temperature at the ends of the rod, and then we want to know how it kind of distributes itself along the rod. Does that make sense so far?
Yeah.
All right, so how would you go about solving this numerically on a computer, right? So you would do something like this. You would basically make some mesh points, really fine mesh points here. So defined mesh points x sub I as being A plus IH, where H is the step. And so if I want to have a certain amount of spacing, right? So let's call this, let's take the spacing to be B minus A over N plus 1. All right. So what happens if you do that? Well, here I want, so I is going to go from 0. When I is 0, I'm at A, right? 1 all the way to N, and then actually all the way to N plus 1, because if I add, when I is N plus 1 and you multiply by H, then N plus 1 cancel. B minus A plus A gives you B, right? So basically, this here, B is xn plus 1, and A is x0. So I kind of rigged it up so that the range 1 through n corresponds to these interior nodes inside in the interval. And then 0 and n plus 1 are the boundary nodes. That makes sense? All right, so we want basically to find, want to approximate and have somehow the yi be very, very close to the actual values of y, where y is the true solution. And of course, then that means that y0 should equal alpha, and then yn plus 1 should equal beta. But the rest of the values of the function yi, these are unknown. These are my unknown, right? So hopefully I can set up a system of equations and solve that system for these unknowns. So the one way to do that is to approximate those derivatives. And one common way to do it is through something called finite differences. Okay, so I'm going to approximate the derivative at xi by taking the value of the function at x, well, it's the approximation to the value of the function at xi plus 1 minus the approximation to the value of the function at a minus 1, and then divide by twice the step. Right, that this is just the difference quotient. This is not true in general. This is the limit of difference quotients. And these are not even the actual difference quotients. They are, they are approximated. But in any case, that's the idea. We are going to think of the derivative at xi as being roughly equal to this. And what about the second derivative? Well, y double prime. Well, the second derivative is the derivative of the derivative, right? So one way to do it is like this. You take the left difference quotient, so yi plus 1 minus yi over h. Subtract the, sorry, I call it the left, the right-hand side of the difference quotient, right? I'm gonna make a picture here, I don't know. Right, so this would be I. Right, so you do a difference quotient on the right minus the difference quotient on the left. That's a difference of difference quotients. And then you divide by h. So in a sense, you're thinking of the difference quotient on the right as being an approximation to the value of the derivative in the middle here. And then the other one is an approximation to the derivative here. So if we take the difference of the derivatives over h now, because it's the middle, that should give us, an approximation for the second derivative. Are you okay with that?
Yeah.
All right.
In general, it makes a lot of sense.
Right. Okay. So let's do a little bit of algebra here because I have a lot of denominators. So in particular, I'm going to get h squared, right? Because I bring this down. And then if I distribute the negative sign here and collect things, so I'm going to get yi plus 1 minus 2yi plus yi. All right, and in both cases, these are linear expressions, right? This is a linear expression, and this is a linear expression. Right, so that's good. That means that we'll be able to now replace this and put it in the equation where I'm going to write pi for the function p at xi, ri for the function r at xi, and pi. So with this notation, for an interior point, okay, what do I get? Let's look at it again. I need to do the second derivative minus p times the first derivative minus q times y equal r, right? So the second derivative already we have, it's right here. And let me multiply everything by h squared. I get yi plus 1 minus then if I multiply everything by h squared, I'm going to have an h here multiplying the term py prime, right? Because one h will cancel, but the other one will remain. So I'm going to have h pi over 2, where I'm using this 2 here. And then that will be times, oh, and there was a minus. So, uh, there's a minus in front of it. Right, that's this term here. I think there was a minus. It was minus, yeah, minus px y prime of x minus qx of y. So that's, all right, and I multiply by h squared, so minus h squared qi yi equal h squared ri. So that makes sense? Hopefully I did the algebra correctly.
Yeah, I'm trying.
All right, so that looks good. And we can actually then collect terms. And so if we collect terms, I claim I'm going to get minus 1/2, 1 plus h let me write it down and then we'll check it. All right, it looks like I've multiplied by negative 1/2 everything, right? And then, so let's look at, for instance, yi minus 1. There's going to be a negative 1/2 yi minus 1. That's this one. And then here, there's a plus HPI over 2 yi minus 1, but that becomes minus HPI over 4, and so that works. Anyways, you go along and you check that this works. But I've also set it up as a system, right? So with the equations in the right order, and you see that it's a band matrix. The matrix of this system will be a band matrix. And if you call these give name to these, like that, then you can set up a vector E will look like this. These are going to be zeros. And then you're going to have, oh, I'm out of time here. So let me just finish this real quick here. A is going to be a band matrix, and it's going to look like this. So it's going to be tridiagonal. All right, so look, make sure that my computations were right and that this works out, how you translate this into this system. Only the first and last term have slightly different inhomogeneous term because they are near the boundary term. But yeah. All right. So we'll continue this example on Wednesday. But make sure that I wrote this correctly.
Okay. Thank you, sir.
Yep.